Karen, you're happy for this to be uploaded to the SuperGen channel, aren't you?
Yeah, I think Mohammed will be all right with it. I can double check with him.
Yeah, if you can, that'd be great. Okay.
So welcome everybody, and so at this Share Network lecture series 3, we have Dr. Karen and Janos, research fellow and TURK team manager at our Translational Energy Research Center, Sheffield, who are going to give us a talk on bioenergy at TURK and also bioenergy with carbon capture and storage utilization. The stage is yours, Karen.
Thank you very much. Yeah, hi everyone, I'm Karen, and I work with my colleague Janos, who's also here, and we're some of the theme managers at the new Translational Energy Research Centre. So I manage the low carbon, sustainable energy and smart energy management themes, and Janos manages biomass, bioenergy, and waste to energy. And we've also got our business development manager here, Alex, as well. So hopefully between us at the end, we should be able to answer all of your questions. So we do a lot of different things at the Translational Energy Research Centre. So because it's the Bioenergy Hub, I'm going to focus on our bioenergy research. And a lot of that is integrated with carbon capture as well. So I'll talk a little bit about that. So I'll do a quick introduction to the new centre and also the centre that we're hopefully going to start building soon, which is for sustainable aviation fuels. I'll then go through the biofuel bioenergy research that we do at TURK, looking at the solid, liquid and gaseous fuels that we use, how we then integrate that with carbon capture, and then look at some of our previous and current research. So some of you might know the PACT facilities that we had in Sheffield. TURK is sort of the bigger, better, newer version of PACT really. So we've moved out of PACT now and we're all in TURK. And so we've done a lot of work looking at wood and comparing it with coal and also comparing it with waste wood as well. So I'll talk a little bit about that research. So first of all, the Translational Energy Research Centre. So this is a national pilot scale facility, and it's a £21 million facility that we have recently just built. And it's one of the largest and best equipped facilities in Europe for this kind of research. It looks at quite a broad range of different areas. So lots of things to help look for green energy that makes it secure, affordable and sustainable for the future. And so this covers bioenergy, but it also covers hydrogen, other zero carbon energy, carbon capture and combustion. And we mainly look at technologies that are a readiness level of 3 to 6 and try to push them a little bit further towards commercialisation. So as I said, we're a £21 million facility, part funded by the ERDF and the UK government. So TURK's main aim is to be a global leader in net zero innovation, and our vision is to be a prominent national centre to develop energy technologies. So not just for today, but also for the options for the future as well. So pushing these different technologies to higher technology readiness levels. We want to make sure that we're looking at resilient and clean energy technologies for the future. And this is the strategy is that this is the next phase of PACT. So you may have been to the PACT facilities, but TURK now has a much more strategic focus, looking at applied research and innovation, and looking at more novel areas of fundamental research, and as it says, driving these technologies closer to be used on a commercial scale. So our research excellence means that we're de-risking innovation, we're mission-orientated research innovation, and we also have lots of flexibility and optionality driven in our approach. So we do tend to be quite commercially focused, and we work with a lot of different organisations. So we work with global companies, so from a range of different sizes, so from small technology startups to multinational global industry partners who are looking for someone who can do research and innovation in their different technology areas. We also work with academic research teams, so other universities, and And so not everybody will be able to, have a facility like TURK at their own organisation. So it means that we can collaborate with other academic institutions with our advanced testing facilities. We also work with leading research and innovation centres and also with regional enterprises, so in particular SMEs in the local area. So this diagram highlights the different research themes that we have at TURK. So the green ones at the top are the ones that are focused on bioenergy. So it's about a quarter of what we do at TURK focuses on bioenergy research. But as you can see, it's all of the different options that we have are very well integrated into the other facilities. So we can use bioenergy, but then we can integrate that into, for example, our carbon capture plants, into our electrolyzers, our methanation plant and things like that. So all of these different themes, whilst they might be quite separate, can be quite linked at TURK. So bioenergy is one of our big focus areas, but we also look at hydrogen, renewable energy, decarbonisation of conventional energy, lots of different options for carbon capture, and particularly carbon utilisation as well. That links in very well with our sustainable and zero carbon fuels, including the sustainable aviation fuels. We also look at energy efficiency, energy storage and smart grids. So such a broad area that we look at within energy. So a brief introduction to the Sustainable Aviation Fuels Innovation Centre. And so this is a building that's going to hopefully be built quite close to TURK. We can take some of the fuels or the feedstocks from TURK and use that for sustainable aviation fuel production. And then the SAF Centre will be able to analyse and characterise those fuels and also look at component testing. So SAF will have a very well-equipped characterisation laboratory, so it can look at various different properties and the compositions of the different sustainable aviation fuels that we either make at TURK or that it will make itself. Okay, so now I'm going to talk a little bit about the different bioenergy options that we have at TURK, so looking at solid, liquid and gaseous fuels. So we have extensive research capabilities for solid fuels. So this is looking at both biomass and bio-wastes, and also looking at combustion and gasification of these fuels. We look at a wide range of particularly industrially relevant fuels. These can be, as you can see in the pictures, either chipped or pelleted fuels, but they're and they can range from what we would say was our nice, clean, high-grade sort of virgin virgin wood fuels, right down to lower qualities of what would be considered waste or bio-waste fuels. So the picture on your right is our combustor facility, and the one on the left is the gasifier, and I'll talk a little bit more about those later. And here we go. So our the facility you can see here is our biomass boiler. It's equipped with waste to energy facilities, and as with all of our facilities on site that generate bioenergy, they can be integrated into our carbon capture system. So all of these systems are BECCS. So this is a 240 kilowatt grate fried boiler. We work very closely with the company that's manufactured this so that we can design it for our research. So that means it's got a lot of ports in at key locations, particularly in the combustion chamber and also in the flue gas pathway. And this means it's really good for characterization. So we can take temperatures, gas samples, things like that at different locations throughout the combustor. We've also got extensive ash collection. So there's the bottom ash comes out underneath the grate. And then the fly ash that we can collect from the multicyclone and then the electrostatic precipitator as well, so we can characterise them. And this has quite a wide range of fuel capabilities, so everything from our nice virgin biomass fuels, which are nice and clean, through the sort of agricultural and forestry wastes, untreated, recycled wood products, and then right down to things like vegetable waste and food processing. So as I said, it's a waste to energy facility. So that means that we are also compliant with the Medium Combustion Plant Directive. So the gasifier that we have is a combined heat and power wood gasifier, and it generates about 50 kilowatts of electrical energy and about 110 kilowatts thermal energy. So it uses wood pellets that you can see here on the left. And the gasification parameters are very tightly controlled, and this means that we can produce a very high quality syngas. So your syngas really wants to be quite a high percentage of CO and hydrogen, and that's what we can generate with this gasifier that you can see here on the left. And then in the middle of the picture there, the smart block is the combined heat and power unit. So this is where the syngas is combusted. So that's how we use the syngas as a fuel, but we can also use the syngas that's produced in our on-site Fischer-Tropsch reactor, and this produces liquid biofuels. In particular, obviously, to interact with our SAF centre, we're mainly focusing this on jet fuels. So for liquid biofuels, we have a biodiesel engine, as you can see here. So this is 188 kilowatts of electrical power that's generated. And this supports, again, a variety of research into the different liquid biofuels that we can use. And as with all of our other facilities, it's instrumented so we can look at the key performance indicators when we're using these different fuels, so we can compare them. And this helps the innovation and development of different green fuels. So in terms of gaseous fuels, so I've just talked about the CHP gasifier and how we can either use the syngas that's produced as a fuel in the CHP unit, or we can use it as a feedstock in our Fischer-Tropsch process. We also have a gas turbine, which you can see in the top right of this picture. So this is 100 kilowatt electrical and 165 kilowatt thermal. It can combust a wide variety of gases, so natural gas or biogas. And these gases can either be real, modulated, or simulated. So this means that we can vary the quality, the composition, the properties of the fuel. So we can use real, either natural gas or biogas. We can modulate them by adding components. So we can include trace elements from a gas cylinder. So for example, sulfurated compounds, if we wanted to look at that. We can also use our large cryogenic storage tanks that we have. So if we wanted to really lower the quality of the fuel, for example, by adding a lot of CO2 into it, we can do that from our cryogenic storage tanks to modulate the biogas, or we could make what we would call 100% simulated gas. So completely synthetic. We just have a specific composition, and we can mix different gases to get to that composition. Okay, so now I'm going to quickly talk about some of the carbon capture options that we have at TURK and how this integrates with our bioenergy facilities. So in that circular diagram I showed earlier, it outlined the full dynamic systems integration we have on site. And that's really important because it means that any bioenergy option we have on site can be combined with any of our carbon capture or utilisation facilities on site as well. So our first carbon capture option is our conventional solvent-based pack column that you can see here on the right. It's a fully instrumented system, and it can capture up to 1 tonne per day of CO2. So those of you who aren't familiar with carbon capture, this conventional system has an absorber column. Our system actually has 2 absorber columns. There's 2 packed beds within each column, so we have 4 packed beds in total, and there's solvent distribution. So the solvent trickles down from the top of the absorber, and the flue gases come up through the bottom, and the CO2 is transferred into our capture solvent. We also have a stripper or desorber column, which we heat the solvent up. So it's a temperature swing CO2 release mechanism from the solvent. And we then get a purer stream of CO2 coming out of that, and then we can recycle the solvent. The system is fully integrated with all of the flue gas generating equipment that we have on site, as well as the gas mixing facility. So not only can we add trace gases or modulate the syngas or biogas that we use on site, we can also inject components into our flue gases as well if we wanted to. So looking at this kind of system, we can do very good comparisons with kind of the baseline scenarios that we would be looking at using conventional solvents in a conventional solvent-based capture system. And we're looking at sort of the evaluation optimization of different solvents for different purposes. Looking at things like degradation studies, which are really important, particularly for biomass, because it does have a lot more interesting composition than some of the sort of coal or natural gas that you would perhaps conventionally have used with this kind of technology. There's also provisions for looking at things like corrosion and materials testing as well. Okay, so the second kind of solvent-based carbon capture we have is a rotating packed bed. This is a next generation technology. It's process intensified, so it has much improved energy performance. So as you can see in this picture with the previous example I was talking about, these columns are very tall and very thin. For a rotating packed bed, to process intensify them, the columns are actually very short and very fat. And so both the absorber and the desorber are both rotating. And again, you have the flue gases coming in the bottom and the liquid solvent coming in the top. The spinning means that the liquid gradually moves out to the edges of the absorber or the desorber, depending on which one you're in, and then is collected in the bottom. And this movement means that we have much better mass transfer. So this improves the energy performance of the system. We also have a molten carbonate fuel cell. Again, this is looking at next generation capture technologies. The difference with this one is actually producing electricity as well as capturing the CO2. And this supports extensive research looking at low carbon energy generation and integrated energy systems, as well as the hydrogen economy. So for all of our bioenergy systems, as well as our capture plants, we have sort of all of the sort of conventional temperature, pressure, flow rate measurements that you might expect to find. We also have a number of analytical probes that we can use in our facilities as well. So things like flame imaging, gas sampling, that kind of thing, corrosion monitoring, deposition probes. We also do all of the standard bulk flue gas analysis, so looking at CO2, unburnt hydrocarbons, acid gases, that sort of thing. We can also look at the gas analysis around the capture process as well, looking at things like nitrous amines and degradation products from the solvent that might escape into the air phase. We also look at entrained metal aerosols. And so this one's really important actually when we're using biomass, because it can have a lot of quite interesting trace elements in it. So we use a state-of-the-art real-time diagnostics to look at the levels and species of these different elements. And when combined with the ash analysis, we can then look at the fate and partitioning of different elements in the system. We can see how changing the operating conditions of the combustors or gasifier impacts on the metal release profile. So, obviously, if you have a very volatile metal, the higher the temperatures, the more we're going to find in an entrained phase. And we can also look at the elements that are in the flue gases that are going into our capture plant, because these are really important to see what impacts these have on the degradation, particularly on the solvents, which is the kind of CO2 capture that we're using at TURK. We also do extensive particulate analysis. So this will give us the particle size distribution, total particle concentration. Our instrument can monitor anything below 10 microns, but we tend to focus on what we would call PM1, which is submicron particles. And the reason for this is because this is what is most likely to escape any particle collection devices, so cyclones, electrostatic precipitators, things like that. They're also probably the most important in terms of the health and environmental impacts as well, if these are escaping from plants. We can also collect the deposited samples within the analyzer and then chemically analyze those, so we can look at all of the different particles, so the bottom ash, the fly ash, and then this superfine particles that we're collecting that will probably have escaped particle collection devices. Okay, so going on to talk about some of the research that we do, so that we have done at PACT and we will continue to do at TURK. So the main research focus we have is looking at minimising energy-related emissions of CO2, primarily through using bioenergy, but by coupling that with carbon capture, it means that we can get close to either net zero or net negative emission systems. And so TURK is demonstrating these technologies at a pilot scale at the moment, and providing sort of this key operational data, which means that projects can scale up and we can have real world impacts, because it means that they'll be able to be used on a commercial level. So we're looking at quite a broad range of different topics at the moment. So moving into sort of this bio waste material, so broadening the scope of what bio means in terms of bioenergy. So in the UK, for example, most of this nice clean white wood that we burn in power stations, it doesn't come from the UK, we're importing it. So if we want to become more self-sustainable in terms of our bioenergy, we need to be looking closer to home. You know, if we have a lot of waste wood, if we have agricultural residues, then all of these could be potentially used to generate bioenergy in the UK. Integrating our bioenergy with carbon capture, building confidence in you know, the technology options for different waste and different carbon capture technologies. And something I've already spoken about is looking at the operational impacts of the bioenergy system, looking at different waste qualities and the impurities that this has on emissions, particularly of the metal aerosols. And then also using all of this experimental data to produce modelling outputs as well. So either computational fluid dynamics, process simulations, techno-economics, life cycle analysis, that sort of thing. And it can be data for inputs for this, or also it can be used to validate these models. Okay, so moving on to our research. So this shows, hopefully these videos are working for you. So this shows some of the flame imaging that we've done. So on the left, we have got air-fired combustion of our pulverized fuels, and on the right, we've got oxy-fuel combustion. So oxy-fuel combustion is a different kind of carbon capture method. So for air-fired combustion, we were firing it in air, so 21% oxygen and a lot of nitrogen, whereas for our oxy-fired cases, we're firing it in a CO2-O2 mix. And we found to get the most similar temperature profiles for combustion, we need to fire with approximately 27% oxygen. So oxy-firing works by having this O2-CO2 mix. And when you have your flue gases coming out, it's primarily CO2. You can condense out the water. You're not trying to separate a small amount of CO2 from a large amount of oxygen, which is what you're doing with post-combustion capture. So you can see the differences between these four videos. So the air-fired coal, for example, the flame is really steady. It's very stable. Whereas for the wood-fired combustion, you can see that it sort of dances around a bit more. It's not quite as stable. And this is because for pulverized fuel combustion, when you're pulverizing coal, you can get quite a tight, small particle size distribution. Whereas for the for the wood-fired case, as you can see, you get quite a large particle size distribution. So the smaller particles are going to burn very quickly, but then you'll have larger particles that will take a lot longer to burn. And so they'll be able to fall further down, but because you might not have an even distribution of these larger particles, it means that the flame does dance a little bit more. You can also see that for the oxy-fired cases, the flame is a lot duller. The air-fired cases, the flames are much brighter. So from this combustion characterization and flame imaging, we can start to build these models. So hopefully if I point with my mouse, you can see, so the burner we have here that sits in the top of this combustor in the pilot scale rig, we can use that for doing lab scale modeling. So looking at things like the gas temperatures and the NOx formation rate. We can also model the burner to look at the velocity profiles within the combustion zone and the temperature profiles as well. So cooler when it's coming in, and then the preheated air that you can see coming through in the middle, and then these red temperatures down the side, which is where the combustion is happening. We can scale that up again. So in an actual power station, they don't have one burner, they have rows and rows and rows of these burners. So we can take the information that we have from these burners and say, well, if we have all of these firing at the same time, what will this look like? And so again, we can model things like temperatures, velocity, that kind of thing. So this is more the CFD modeling side of things, but we can then take this sort of cross section here of this combustion chamber. So that's like a slice through this combustor, and we can use that. So that's a rate controlling component, the combustor, and we can put that within a model of a power station. So this shows the whole power station here. So we've got the air and the fuel coming in. We've got our steam turbines in a line over here. We've got our stack. We've got our gas cleaning equipment. And so we can use that rate controlling component to integrate that with our process simulations. So of the capture plant, that can be integrated with the power plant as well. So we can look at full chain VEX, full chain bioenergy and carbon capture. So we've also done some work looking at these metaerosol emissions that we get. So looking at the fuel composition up here, we can see that our biomass had around 10 times more potassium than our coal. And so you would expect higher levels of potassium in our biomass flue gas, which is exactly what we've seen. We see these peaks periodically throughout, and this could be because the potassium that's contained within our fuel is not evenly distributed. So if we have larger particles that contain more potassium, that could make our potassium readings really spike. And we can also compare our air-fired cases and our oxy-fired cases. And we found that for biomass, the oxy-firing meant that our potassium release was much, much higher than for our air-fired biomass cases. So this is the combustor that I showed you earlier. So this is now our wood versus waste wood with carbon capture. So we did some tests looking at short rotation coppice willow and grade A waste wood. So I said about the ports that we worked with the company to get these ports put in. So these numbers here are all different ports. And this chart here on the right shows the temperatures at each of those different locations. So you can see as you go through the combustion chamber and then up round the second pass and into the heat exchanger at the top, how the temperature profiles change. And again, we looked at various different elements that are found as metaerosols in the flue gases. So the fuel analysis showed that the willow had very high levels of potassium and also zinc, and the waste wood had slightly more lead and a lot more sodium in it. And so whilst this kind of information is really important to have, it gives us an indication of what we should be looking for in our flue gases. The concentrations that we find in our fuel don't necessarily always translate into equivalent emissions in terms of metaerosols. So for potassium, for example, we do see considerably more potassium in our willow flue gases than we do in our waste wood. But for zinc, for example, we had a lot more zinc in our willow, whereas actually the peak for the waste wood was significantly higher. And so this is just an average value for our fuel analysis. So whilst this average value, is for quite a large sample, when you have, small particles which have a very high zinc concentration, it does mean that our our peak emissions are much greater than the average emissions, which were quite considerably lower for the waste wood. Okay, so just in summary, we have a wide range of biomass and bioenergy equipment to use at our TURK facilities, and we can use these with a wide range of different fuels. So some of the ones here I've spoken about are nice clean virgin woods, right through to the sort of dirtier bio-waste materials. We have many analytical probes to use with all of our facilities, as well as our comprehensive flue gas analysis. So looking at capabilities for gas species, entrained metal aerosols and particle emissions, so we can fully characterise the process. All of these can be integrated with all of our different carbon capture options and utilisation. And something that is really important for TURK is the visiting bays that we have. So we have spaces in the yard outside for additional equipment to be brought in. So if you guys have something, a combustor, a fuel, anything that you would like to test, you can bring it in, and it's a pretty plug and play system. Everything is already integrated into the bays. So if you have a combustor, you can plug it in and we can do carbon capture from it. So there's lots of collaboration opportunities out there for all of you to work with us. So I'll say thank you for listening. If you have any questions, we're happy to answer them, but our email addresses are there as well. And our website is TURK, TERC.
Thank you very much, Karen. Very good talk. Is there any questions? I think we could stop recording now, and so we can feel free to ask any questions or